Right, for 5C, which is lenses, we're going to look at the different types of lens. So obviously there are two types of lens, and we need to know what those two types are, what their names are, and what they do to light as light passes through. We're going to look at the power of a lens. So what is the definition of the power of a lens, and how we can change the power, and what that affects the image formed, or how that affects light that passes through. And then what we're going to look at actually is some diagrams, what we can draw for light passing through a for different objects, and how the image that might be formed, how it would be formed through that lens. So that'll make a little bit more sense as we move through. The first thing that we're going to look at is the two types of lens. So categorically there are two types of lens that we need to know about. One of which is called a convex lens, which actually has another name which is converging, and that name converging actually will make more sense when we see the diagram. So a convex lens, also known as a converging lens, and the definition is, for a convex lens, light is refracted through the lens and focused to a single point. Okay, and again that will make more sense when we actually look at the diagram, but essentially as light passes through a convex lens, the light is going to refract, which means it will change direction. It's actually going to come together towards what we call the principal axis, and it's going to focus together at a single point. The alternative is a concave, also known as a diverging lens. So a concave or diverging lens is when light is refracted through the lens, but it leaves the lens in different directions. It actually refracts away and outwards when it passes through that lens. Now, if we want to determine which one is which, really, we just need to make our own assumption of what concave might mean. This one here on the left is a concave lens. So concave or diverging is this one. Now, the easiest way really to remember that is kind of it concaves in, it caves in. That's the only and most simple way. If you have another way of remembering that, it's entirely your choice. But concave is this curved inward lens like this, and the convex or the converging lens is the one that actually curves out. So it's the one that comes out. So concave is the one that has that cave-like shape on the inside, so it curves inward, and the convex is the lens that curves outwards. Now, what happens to light when it passes through each of these lenses? That's the most important thing. That's what we want to know, what happens when light passes through these specific types of lens. As we mentioned, you've got the principal axis, which passes straight through the center of that lens. So if the light rays enter the lens parallel to the axis, so this is the most basic diagram that you might be expected to draw, is when the light rays enter parallel to the axis, they then pass through the lens, they refract. This is a convex lens, which means that the light rays refract towards the axis. So they refract towards the axis, and they actually cross over at this single point here. But of course they're going to carry on through that. So they do carry on through, but that point there where they actually come together is the point that we're really focusing on. Now this is called the focus, or also known as the focal point. So the point at which light rays converge, i.e. come together, hence the name, converging lens, the point at which those light rays come together and converge is known as the focal point. Now if we take that focal point, we can actually say that the distance from the center of the lens to that focal point for this specific lens is known as the focal length. Now every lens will have a different focal length. What that means is every lens will refract the light by different amounts so that it crosses the axis at a different point. For example, some convex lenses may have a focal point here, which means the focal point is closer to the lens. That means that the light has refracted more or at a greater angle, and therefore the focal length would be shorter. Okay? Alternatively, you may have a different lens that actually doesn't refract the light quite as much as this. So the light rays meet somewhere further out here. So they all cross at this point here. That would be the focal point. Therefore, you'd have a much longer focal length. Now, the amount at which a lens will refract the light. So in this instance, the focal length is around 2.5 squares. In fact, it's 3 squares exactly. So the focal length is 3 squares. That means the refraction of light through this length was a certain amount. But if a lens refracted the light more, so if there was more refraction taking place when it passed through the lens, then you'd say that the lens is more powerful. So we will look again in a second, but the definition of the power of a lens is how much the lens refracts the light. So more refraction would mean that the lens is more powerful. if that happened, so the consequence of having a more powerful lens and therefore the light refracting more, the consequence would be that it would refract and it would actually cross at a closer point to the lens. Now, if it's crossing at a closer point to the lens, if it's more powerful, then that means that the focal length is shorter. So the power of a lens is specifically how much refraction occurs when the light passes through. So the more powerful the lens, the more refraction. If the lens is more powerful, more refraction occurs, then the focal length is shorter because those rays meet at a point closer to the lens. So more power, more refraction, therefore shorter focal length. Now, what would a more powerful lens look like in comparison to this convex lens? How would I actually draw, or what would a real lens look like if it was more powerful to this lens? And all it is the thickness or the curvature of the lens. So if you had a thicker lens, so it kind of curved out at the edges more, so it had a greater curvature, a thicker lens would be a more powerful lens. So thicker lens, more powerful; thinner lens, less powerful. If it's more powerful, it refracts light more. If it's less powerful, it refracts light less. And obviously, if it's more powerful, then it has a shorter focal length. And if it's less powerful, it has a longer focal length. Okay? And that's all we need for this first simple diagram through the convex lens. Now, if we were to draw the same diagram and ask ourselves, well, what would happen then if the light came in parallel to the concave lens or diverging lens? And obviously we had a definition of this, which was the light actually refracts away and in different directions. So if we draw light coming in and they refract away, the one in the center obviously passed straight through because it came in at 90 degrees to the lens, so it didn't actually refract. But all the other rays refract away from the lens. This is a concave or diverging lens. Now, you might assume that comparing it to the last diagram, there is no focal point through a concave lens. That's true on this side of the lens. So after the lens, there is no focal point because these rays will never come together. However, if we follow these rays back through the lens to the same side as the light came in, like this, then actually they would meet at this point. Now, because these rays aren't actually coming back through the lens, we draw them as dashed lines. But essentially what we're saying is if we were to draw the diagram so that the rays came back through the lens and they did focus at this point, then that would be what's known as a virtual focal point. Because this point here where we've drawn the rays coming together is not actually where they do come together. So it is a virtual focal point, and therefore you have a virtual focal length. Okay? So virtual really means when the image or the focus is on the same side of the lens as the light came in. Whereas in the previous example, we said that the focal point and focal length was, this is a real focal point and focal length because the light rays actually came together and they converged after the lens. So the light came in on this side and they focused on the other side. But in the concave, the light came in this side, they didn't converge on the other side, but we drew it back so that the focal point was on the same side as the light came in. That's a virtual focal point. Now, just having a look at two images in terms of what's the difference then between a virtual focal point and a real focal point. This is an image of basically a window. So if I put a lens, let's say the light coming through the window here, and I put a lens here, and I had the screen here, or even the whiteboard for example, then the light from the window would pass through my lens, and it would create an image on a piece of paper or on a screen on the other side of the lens. Yes, it's upside down. We're going to consider why it's upside down in the future. But just looking at object, which is the window, light passes through the lens and creates an image on the other side of the lens. That's a real image. Okay? A real image is an image that can be projected onto a screen. So if we just look at the definitions of real and virtual, real images can be projected onto a screen. But if we wanted to talk in terms of the diagram itself, the light from the object came into the lens from the left, it refracted and passed through the lens, and it focused on the screen on the other side of the lens. That's real. Now if we take the magnifying glass for example, magnifying glass, behind the magnifying glass is some grass. So it's just any object really, but in this case it's grass. So we're looking at grass through a magnifying glass, and basically the image that we're seeing is through the magnifying glass. So the image we know is going to be magnified, which is bigger. So we know that the image that we're seeing is bigger than the real grass behind, but the image of the glass that we're looking at is on the same side of the lens as the object itself. That is a virtual image, okay? Because this image that we're looking at right now through this magnifying glass cannot be projected onto a screen, and it was formed on the same side of the lens that the object was as well. So that's virtual. This one is real. This image here of the window is real image on the screen. This image of the glass through the magnifying glass is a virtual image because we cannot project it onto a screen, and it was formed on the same side of the lens as the object itself. Now, there's a few words that we need to actually use to refer to an image that is formed through a lens when we look at it. So what would the features of the image be? Diminished, which means smaller, and you can clearly see the window is this big, but the image of the window is smaller, so it's diminished, means smaller. It's inverted, which means it's upside down. So you can clearly see the window should be the right way, but on the screen it's upside down. So diminished meaning smaller, inverted, which is upside down, and it's real because, as we said, the image was formed after the lens. So diminished, inverted, and real. Whereas for the magnifying glass, we're looking at an image here which is magnified, so bigger, which is magnified, upright, so it's not upside down, it is the right way that it should be, which is upright, and finally we said that this image is a virtual image. Now, if we take these three things for both images, we would say every single time we draw a diagram or we're asked the question, here is an object seen through a lens, what would the image be? So if an image is formed, what would that image look like? And the first thing you have to ask yourself is, what's the size? Is it larger than the object? So is it magnified? Or is it smaller than the object, in which case is it diminished? Or is it the same size? Because you do get images which are exactly the same size as the object as well. So diminished, magnified, same size. The second thing you ask yourself is it the right way up or is it upside down? I.e., is it inverted or is it upright? So you ask yourself, is it upside down, is it inverted, or is it upright? And then the third one is it a real or is it a virtual image? And in a diagram we can show in a second that the easiest way to tell if it's a real or virtual image is if the image was formed after the lens or on the same side of the lens as the image, okay? So is it diminished, magnified, or same size? Is it inverted or upright? Is it real or virtual? And also one more factor that we're going to actually establish in the next diagrams is, where is the image actually formed? Like, how far away from the lens is the image formed compared to how far away from the lens the object was? Okay? So we did just look at power quite briefly. We said that the power of a lens tells you how much it refracts the light. The more refraction, the more powerful. The more refraction and therefore the more powerful, the shorter the focal length, and a lens specifically is more powerful if it's thicker. Okay, so the thicker the lens, the more powerful, the more refraction, and the more refraction, the shorter the focal length. Complete opposite, the thinner the lens, the less powerful, the less refraction, the longer the focal length. Okay? We're going to move on to the very last diagrams that we can draw. So we already drew the simple diagram of a lens where the rays came in parallel to the axis and they refract through the lens either to the axis if it's convex, or they diverged and refracted away. But they came in parallel, and that was simply a diagram that we used to determine where the focal point of that lens is. Now, we just established that there are two types of image that can be formed through a lens. Real or virtual, also the size, whether it's upside down or upright. These diagrams will help us determine what image will be formed of an object when it's passed through the lens, okay? And how you know that this diagram is a different diagram to the initial one where parallel rays came in and just refract through is because in this one we have F and 2F. On both sides, these are the real sides. If the light of the object came in from this side and it formed over here, you've got F and 2F, which is real. But if the image is formed on this side, which is the same side of the lens as the object, then you're going to get a virtual image. Now, the 2F is simply 2 times the focal length. And the only reason we've drawn that is because it is a significant length when we're determining what the image formed might look like. Okay? The only difference between this diagram now and the initial one is we've got 2F and 2F on both sides. This focal point is 2 squares away from the lens, therefore double that, this one is 4 squares away. And we'll see why that's important in a second. So on my diagram, I draw an arrow above the axis of the object that I am going to look at through a lens. Okay, I'm going to look at the image formed of this object through the lens. So my object is just simply an arrow in green, 2 squares up. Just as long as it's not higher than the lens, then it's easy to do. So we draw the object just below the height of the lens. Obviously it's not quite to scale. And there's my object. Now I want to know, this object could be anything. It could be me. So for example, somebody looking at me outside of 2f. 2f is the focal length of a lens. Now it could be that close to my eye. The focal length could be that long, so twice the focal length would be that long. Most things that you look at through your eyes are outside 2f. Okay, so that's where we're going to start. Anything you see around you is an object like this outside of 2f. But what's the image formed on your retina in your eye of this object? 2 rays we need. So we must use 2 rays on this diagram. We're going to add 2 rays to the diagram so that we can determine, number 1, is there an image formed? And 2, what will that image look like? Okay, so 2 rays are required to complete this diagram. Ray number 1, parallel to the axis. So you draw your first ray parallel to the axis, and when it hits this convex lens, we know that it will refract, but we're going to make sure that it refracts through the focal point. Okay, so ray number 1 in these diagrams, parallel to the axis, refracts through F. That's the first ray done. Every single time you have a diagram with a lens, F and 2F, and an object on one side of the lens, and the exam question says, draw a diagram to determine what image would be formed of this object through this lens, then ray number 1 is parallel to the axis, refracts through F. It doesn't matter where this object is. We're going to see in a second. We can move it here, here, at F, inside F. It doesn't matter where the object is. Your first ray is always parallel to the axis and refracts through F. Ray number 2, even easier than this one. Ray number 2 simply goes straight through the center of the lens. Okay? There are millions and millions of light rays leaving this object. Every time light hits an object, it's diffuse reflection, the light scatters off, but there are millions. I only need 2 to tell me what image will be formed. So number 1, parallel to axis, refract through F. Ray number 2, straight through the center of the lens. Quite clearly, the 2 rays cross over at this point here. Now I know, looking at this straight away, an image is going to be formed. The image is going to be formed at the point where the light rays cross over. So if they cross over, an image is formed. And where that image will be formed, we draw with another green arrow. So the object arrow is above the axis all the time on this side of the lens. The image is from the point where the 2 rays cross, up or down, but in this case up to the axis, or from the axis to that point where they cross. Now, this is all we need to tell us what has happened to this image. Okay? This arrow here is the image. This arrow here is the object. Is this image real or virtual? It's after the lens. So the object is this side, the image is formed on the other side of the lens. This is a real image. Is it bigger, smaller, or the same size? Well, have a look at the arrow. That is the size of the image. Compared to the size of the object is bigger. So my image is smaller, meaning that my image is diminished. So it's real, it's diminished. Is it upright or is it inverted? Clearly, this image is below the principal axis. If the image is below the axis, then it's inverted. It's upside down. So this is real, it's diminished, it's smaller, and it's inverted. The fourth thing that I can say about it, which is again the least important, but I can at least still say it, this image is formed between F and 2F, whereas the object was actually outside 2F. And an example in real life of this would be literally if you were looking at the moon. If you look at the moon tonight with your own eyes, then the object of the moon is 3.8 million kilometers away. That's clearly outside 2F, millions of kilometers outside 2F. And the image formed on the back of your eye and your retina will be formed between F and 2F. The image of the moon on your eye, if you look at it tonight, will be between F and 2F. It will be a real image. It will be inverted on your retina, and it will be diminished. The moon itself is enormous, around 3,500 kilometers in diameter. Okay? the image that you get on your eye has to fit onto your retina, so it's obviously diminished. The interesting thing about your brain though, when your brain produces an inverted image on the back of your retina, your brain actually basically flips that image if you want, it turns it back the right way. So the image of the moon or anything you see with your eyes technically is inverted on your retina, but your brain flips it because it knows it's inverted and therefore it turns it the right way for you. But in terms of just the image formed, it should be inverted according to this. Let's try another one. If I move the object this time so that it's at 2f, so before it was any object outside of twice the focal length of my lens, all images would be produced, real, inverted, diminished, and between f and 2f. What if the object was at 2f? What would the image formed look like? Ray number 1, parallel to axis, refract through f. Okay? Ray number 2, straight through the center of the lens. Do they cross at a single point? Yes. Do they cross on the other side? Let's draw the image in at the point where they cross. It so happens that it's actually at 2f, which is our 4th point. So this is the image formed. Let's discuss the image formed. 1, it's after the lens, so it's real. It's not virtual, it's real. 2, it turns out that this image is exactly the same size as the object, so it's the same size. It's not diminished, it's not magnified, it's the same size. Again, it's below the axis, so it's inverted. And finally, where is it? We said here, this one is actually at 2f. And a real example of this, where you produce an image exactly the same size as the object, for example, a photocopier. You copy a piece of paper exactly the same size, so this would be what happens inside a photocopier. Okay? Another one. Let's put the object between f and 2f. 2 rays, parallel through f. Straight through the center. Do they cross? Yes, they do. They cross down here, right outside 2f this time. So we'll draw our image on our diagram. Let's consider this image. Is it real? Yes, because it's formed on the other side of the lens. This is a real image. Is it bigger, smaller, or the same size? This image is actually bigger than the object itself. Okay, so this image is magnified. It's real, it's magnified. Again, it's upside down, so it's inverted, and it's produced outside 2f. Now, where in real life might I experience having an object produce an image through a lens which is further away, it's bigger, but it's still inverted? A cinema screen, a projector. Okay, you'd have to have something in the projector that flips it the right way, but you would produce a bigger image of the film onto a screen much further away. Okay, so this example is actually seen in the cinemas in a projector, but we have to invert it ourselves, just like our brain has to invert the image that is on our retina. Another example, put the object at f. So put it on the focal point. First ray is parallel and through f. Second ray is straight through the center. Now, interestingly, this diagram produces 2 parallel rays. 2 parallel rays will never cross. Now, if they never cross, no image is formed. No real image, no virtual image. Even if I went back, they're parallel, so they will never ever form an image. This essentially in real life is like a torch or a flashlight, okay, or a floodlight, a stadium light. It produces light that goes on and on and on to infinity. It will never ever cross, so no image will ever be formed. Finally, through the convex lens, we'll put the object inside the focal point. Same procedure, ray number 1, parallel to axis and through f, through the center. Now again, these rays will not meet after the lens, but they're not parallel to one another, so we could draw them back like we did in the first diagram for the concave lens. We draw them back through the lens where they do come together on this side. And if they do come together on this side, we can draw the object from the axis to this point where they cross, and this image will be virtual. The reason that this image is virtual is because the light rays cross on the same side of the lens as the object. So it's not real, it's not on this side, it's a virtual image, which we know means it cannot be projected onto a screen. And actually, if we look at the other features, it's a virtual image because it's on the same side as the object. It's clearly a magnified image because it's much, much taller than the object. So it's a magnification, it's magnified. It's actually upright, it's not upside down, it's above the axis, so it's upright, and it's produced just between f and 2f, further away than the object was itself. So in real life, what would this be? This is a magnifying glass. If you look at an object through a magnifying glass, so through the lens this way, the object is here, quite small, close to the lens. It will produce an enlarged, magnified image in the right upright position, a little bit further away actually to the real object itself. So when we were looking at the grass through the magnifying glass, this is grass on the other side as an object, rays coming through but not meeting on this side, going back through the lens and meeting on the same side to produce a upright, magnified, virtual image which is a little bit further away than the grass. So technically what you're seeing there is bigger than it should be, but it's also a little bit further away than it would be. So the grass itself is actually a little bit closer than what this suggests. So those are all the diagrams you can draw for a convex lens, an object on one side. What would the image look like if the light rays passed through the lens? Only other one that you can draw is what would an image be produced if the light of an object went through a concave lens. So let's just put the object between f and 2f. I can tell you now, if you were to do this diagram for the object at any position, it would not make a difference, and you can try that and draw the different diagrams. Ray number 1 comes parallel to the axis. However, in a concave lens, the light will not refract through f, because a concave lens diverges the light, so it will refract away from the lens, meaning it goes up there. But, just like on the first diagram, if we follow that ray back, it will come through this focal point. So on a concave lens, parallel to the axis, refracts away from the lens, but it will then come through back through the lens as a virtual line to the focal point on the left side. Second one the same again, straight through the center of the lens. Now, no light rays are going to cross on this side, but they do cross one of my virtual lines with the real ray on this side, giving me an image produced from the axis to here. So what is the image produced through a concave lens? Always virtual, because they don't cross on this side, but they do on this side, so it's a virtual image. It's upright, because it's above the axis. It's diminished, it's clearly smaller than the object, and it is actually inside the focal point. No matter where you put that object, if you put it outside 2f, at 2f, at f, or inside f, you will get this diagram, this image every single time, and you can try that and follow the rays. It will be virtual, upright, diminished, and inside the focal point. Okay? And that's all the different lens diagrams you can draw. The last thing to consider on lenses, if you want to go a step further and you want to actually look at the different things that your eye can do, or the different problems that people have with their eyes, there's two types of poor eyesight essentially. If you have bad eyes, first and foremost, every single person with an eye has a lens. The lens in the eye is a convex lens. It converges the light at the retina. So your retina is the place where the image is produced on the screen. If the lens of a certain person is too powerful, which means it's maybe too thick or the curvature is too large, then it's going to bring that light in too close, it's going to refract it too much, meaning that the focal point or the focal length will be too short, and where it should hit the retina, it's meeting just before. So it actually crosses, look, just before the retina, because the lens is a little bit too powerful, so it refracts it too much, the focal length is too short. It focuses the light just before. Now the way to fix that, and this is known as myopia or short-sightedness, okay? So you can see close objects quite clearly, but the farther distant objects are quite blurred. This tends to happen in young people as well. So younger people tend to suffer from myopia or short-sightedness, meaning that their lens is too powerful and it's refracting the light too soon before the retina. Now how do we fix that? Obviously we use glasses with lenses, or you can even use contact lenses, but the lens that must be used for this situation is a concave lens. Because the reason is when it goes through the first glasses of the concave lens, it spreads the light out slightly, and then when it hits the lens, which is stronger than the normal lens, it will now refract the lens at the right point, right at the back of the retina, okay? So for someone with myopia or short sight where the lens is too powerful and the rays meet too soon, we use a concave lens to spread them out, and then they meet at the retina. Now the opposite of that is hyperopia, okay? Someone who suffers from long sight, they see far distances quite clearly, but the objects that are close are quite blurred. The reason for that is their lens, and this happens again in people as you get older, so older people tend to suffer from hyperopia, because the refraction is not strong enough, their lens is not strong enough, that the refraction takes place, but it doesn't cross at the retina, it will cross behind the retina, okay? Now how can we get the light that's refracting behind the retina to come further forward, so reduce the focal length and bring that light together closer? We use a convex lens, so when the light comes in, it brings it closer together just before the eye, and then the eye brings it closer together again, perfectly at the retina, okay? So that's short-sightedness, and this is long-sightedness, and that essentially is the whole of 5C and lenses.